Okay, this is lecture 19. So let's start. Are there any questions based on what I did last time? So in the notes, in some version, maybe the next one which I will upload, I've given an exercise to derive the formula for a correlation function in quantum mechanics. So probably if I had wanted to make yesterday's lecture easier for you, I would have derived a formula for this kind of thing. In terms of path integrals, and we would have found that it is the limit t goes to infinity times some normalization times the path integral where this integral is performed over paths which start at xi at the time close to minus infinity and end at point xf. Okay. So this formula is essentially what I did yesterday with scalar field theory. The difference is that it's much easier to do this, and the key difference, and this might make things a little easier for you, is that the complete set of states in terms of position eigenstates is a simple integral in dx of the position eigenstate xx. Okay, you can give it a time also, some t, so you can even write this as x a t a x a t a. This formula is simple because this is a position eigenstate, something we study in quantum mechanics. We can integrate that amounts to the same as summing because they are continuous eigenvalues. So the sum over complete set is becomes an integral, and then that integral is 1 by completeness. And this is the quantity you would want to insert once at each of the times t1 up to tn on this side, after picking a time ordering, and then evaluate each of these operators on a corresponding state, and then with a little bit of work you would end up with this. So the same process, so this is left for you as an exercise, it's not difficult, and once you understand that, then in the only real extra step is that in QFT, the analog of a complete set of position eigenstates is already a path integral and this. Where this state represents an entire function phi a of x. That means the operator phi hat acting on this will return the answer phi a of x. Okay. And then this integral is over all spatial configurations, that is configuration all functions of x at a fixed time. Sometime a few lectures ago I had mentioned that such an integral can be done by picking a compact space like a sphere or something and then going to some basis of spherical harmonics. And with what we know is that on the sphere, all functions, on the two sphere, all functions can just be written as linear combinations of spherical harmonics. Okay, on the torus they can be written as functions of some simple trigonometric thing like sine and cos. If it's a three sphere, then there are some three sphere version. You can have spherical harmonics in any sphere of any dimension. So since in these applications the space is three-dimensional and time is one more, so we could imagine that space, instead of being open 3D space, is some three sphere. Then we can give this kind of completeness relation, very precise definition. Yes.
In that case, what about the Lorentz invariance?
Yeah, so this process will not be Lorentz invariant because here we are inserting a complete set of states at a fixed time. And that's part of the statement that the operator formalism is never manifestly Lorentz invariant, because in any case we are trying to calculate these things with some insertion of Hamiltonian, and Hamiltonian itself is depends on a choice of time.
But so you're saying that since they are going to be eliminated from the final form,
Yeah.
the final form will be Lorentz
Exactly.
invariant, but
So what will happen is that two problems will cancel out. This integral is over all functions at a given time, but after we calculate the analog of this amplitude for field theory, we will have a path integral over paths which have fixed values at those times. And then these integrals will integrate over those fixed values. So whatever was a problem with those paths, that the paths were not unrestricted but they were restricted to pass through certain functions on the way, that will be removed by integrating over those functions. And so at the end, everything is Lorentz invariant. So even with insertions of operators, the answer is Lorentz invariant in field theory. I don't want to confuse you. I started by saying something about quantum mechanics. I'm just saying that if you do this exercise, you will be well prepared to go through the notes of yesterday, which are about field theory. And in the field theory context, the question that he asked is relevant about Lorentz invariance. Okay, this is a simpler version of the exercise. The main difference between this exercise and the field theory case is that when I have a fixed time in quantum mechanics, then the particle can have an arbitrary position. But in field theory, when I am at a fixed time, the field can be an arbitrary function of x. Just fixing the time doesn't just leave a position available, it leaves all functions of x at that time. So then to integrate this set of states to get a completeness relation saying that it's 1, I have to integrate over all functions. So it's already a path integral but a space path integral. While in the quantum mechanical case, it's an ordinary integral. So this is easier, that's all. So if you do this exercise, then yesterday's lecture will become sort of trivial. Maybe if I had to do it all over again, I might have done this in class and asked you to generalize it to the path integral, to the field theory case. Can do it either way. Anyway, the upshot of all this is a very nice formula, and we are going to apply that formula today so first we'll remember what's the formula. The formula for field theory. So I'm working in scalar field theory, and actually yesterday I put some indices on the field, but it's easiest to just assume that my scalar field theory has just one field, one real field. Of course, you know that it can have any number of fields, but then we have to do a path integral over all of them, right? So, and to simplify my notation, there's just path integral over d phi, where phi is one scalar field, and then I'm looking for correlation functions of that same phi. And the formula which we sort of derived, nothing is ever derived in path integrals, it's just motivated, is that the normalized version of this is equal to the path integral d phi e to the is of phi, the function phi x1 t1 up to phi xn tn upon the same thing without those insertions. And both these quantities have a simpler name. I'll just call them phi of x1 t1 up to phi at xn tn inside a bracket without saying what the bracket is. My convention is that when I write such a thing as the top, I mean a normalized one. Okay, so if it's in operator formalism, then that thing is the normalized time ordered expectation value normalized by this. If it's being done in path integral, then it's this quantity normalized by this. And yesterday our argument was that this side is equal to that side. So there are two alternate ways of calculating the same quantity. We'll also give it a name. We'll just call it g of x. Okay. Instead of distinguishing, I think at this stage I won't distinguish space and time, so I'll just write x1, where x1 is the 4 vector position. So if I call it G, okay, G I have actually used for something else. I won't call it G. I think we'll always just call it this. So it's the normalized object. And now today our goal is calculate it. Okay. And to do that, we'll recall how we ever calculated any path integral. Wherever we discussed path integrals and their calculation, the steps were expand whatever is the variable. In this case, it is a scalar field phi. So phi as phi classical plus eta. Okay. Then up to quadratic term. We get a determinant. And 3, which we have never really discussed so far, beyond, I said some words about beyond quadratic term, but today we'll do that. So this is called perturbation series. And this is a classical solution. Very often in the research literature, it's called a saddle point. And sometimes it's easy to see what classical solution we should use. Sometimes it's more subtle. Okay, there's a wide range of problems to which this formalism can be applied. They cover scalar fields, vector fields, fermion fields, gravity fields. Entire literature of work by Gibbons and Hawking in the 1970s and 80s, probably 80s, is on trying to study gravity in the path integral formalism. It's called Euclidean gravity. And you can't do anything exactly in that case, but actually you can't do anything exactly in almost any case. And with some approximations, they came up with some very, very interesting results in the field of gravity outside the scope of these lectures. But the important point is that what they did also conformed to this 3-step process. Everybody basically conforms to this process. One is find a classical solution, then expand. Then second is, if you keep this expansion parameter eta, this fluctuation or deviation field, if you keep up to quadratic order, then you will get a determinant, which we have seen already a few times and we'll see once more. And then if you keep beyond quadratic order, you get a perturbation series. So the full answer that we get in this way is the product of 3 answers, because this first part gives me a factor e to the I s classical of my solution. So I can call it s of phi classical. The action has to be evaluated on the classical solution, and that in the path integral from here, that will come outside. Okay. Of course, it may cancel with what is in the denominator, so those are all things we have to worry about. But in principle, we'll be calculating the numerator separately and then only dividing by denominator. So this is a factor you can get. There's a determinant factor. We called it det O, sometimes we called it det to the minus half of O. We'll be seeing it today. And then this doesn't have a simple name, doesn't have a simple mathematical name, but the words for it is Feynman diagrams. So the predictions of a field theory path integral are the classical action, which comes as a phase in front, the determinant, and the Feynman diagrams. 3 things. Okay. In the most naive or most simple systems, this may be trivial or it may cancel. This will not be trivial, but it may cancel. For example, when I divide things like this, and only these are left. And that's why in QFT1, the only thing that you actually had to learn was Feynman diagrams. So now what you're realizing is that that's one out of three different things we have to do in principle. This could be important, this could be important, this could be important. All depends on the problem and how strong we are in solving it. Did I ever start the video? Thank goodness. Sometimes I have dreams that I forgot to start it and I'll have to give the lecture again. Good. Okay, so keep this sort of picture in mind that there are three parts to the calculation. Okay, so now let's immediately start with calculating that right hand side thing. So let me rewrite it here. And let's see how it's done. So we want to calculate this, this, and then this. Okay, so the trick to calculate this is to define integral d phi e to the I s of phi plus integral j of x phi of x d for x. I think we briefly discussed this in the context of quantum mechanics, something similar, but now we'll actually go into a little bit more detail. Okay. And this quantity, if that was not there, it would just be what we call the vacuum path integral, namely d phi over e to the is with nothing else inserted. That usually goes by the name of z because it's related to the partition function. But now z is a functional of j because I've introduced an external source j. And now we have some standard things we can do with this. Actually, maybe I just went a little too fast. We shouldn't introduce the source right now because if you remember, the path integral is not really done over phi but over the fluctuation eta, which might be phi or it might not be phi. So first we have to discuss the first step, writing phi of x as phi classical of x plus eta of x. So what should be phi classical? Now in the quantum mechanical case, we saw some examples of phi classicals or x classicals, which were some paths that started somewhere and ended somewhere. And the question is, what should we do in field theory? And in fact, what boundary conditions should we give? So in path integrals, in quantum mechanics, we said that the particle starts at a position xi and ends at a position xf. That's what you can say. In field theory, we'll think of it a little bit differently. So let's imagine that S of phi is of the form integral d for x minus some potential. Now what we would like is that as t goes to minus infinity t, the classical solution phi classical of x and t should go to a classical vacuum. And that is basically something which minimizes the energy. So what's the energy in this system? The energy, which is same as Hamiltonian if you like, is Hamiltonian density is pi squared upon 2, so what is it, half pi squared plus half gradient of phi squared plus m squared by 2 phi squared plus lead phi, and we should minimize this. Why should we minimize this? Well, it's part of the same thing that we did yesterday when we showed that if you go to the far past, basically you project into the vacuum. Okay, this is basically the same idea, and it should be clear because supposing in the far past, supposing at a time t equal to, I don't know, minus 100 years, my field went into some configuration which did not minimize this, okay, then what would be the energy of that field when I integrate over d for x? Okay, supposing it had some constant energy which was not a minimum of this thing, then when I integrate that constant energy over all space and time, I'll just get a huge divergence. Okay, so that's not a good choice. So if I want my configuration to make, if I want my field theory to make sense, I would like that the energy density be as close to zero as possible in the far past and the far future. And that's what I mean by classical vacuum. And we'll see many examples. In the next few lectures, we'll see many different field theories, and in each of them, we'll see what should be the classical vacuum. Okay, but just it's something which minimizes the energy. Yes.
So, but in like if we have a 0 point energy,
Yeah.
then
Yeah.
irrespective of what the it is going
Yeah,
to have.
yeah. So of course, if we have a 0 point energy, which we generically have, then you cannot really have zero energy in the past. But you can, so first thing is that this is all classical. We're talking of the boundary conditions on a classical solution. So in this case, we don't have to think about 0 point energy. That will be a problem to address when we quantize eta. Remember that we are only going to quantize eta and not the whole thing. Okay, so let's,
classically,
so
phi equal to 0 is a correct.
phi equals 0 is good.
Okay.
It might be that for some reason my field theory has a constant energy in it, then phi might not be 0 but some other constant. That those kind of things I can adjust to, and sometimes that has a physical meaning.
But
Okay,
what
yeah.
if V of like there is a potential there?
Yeah.
So what if V of 0 is not 0?
Exactly. So if supposing there's some value phi 0 for which V is 0, then phi should go to that value. In fact, to make this simpler, I'll incorporate the mass term into V. So I won't write it separately. And now classical vacuum is simply the minimum of V of phi. Okay. So it's some constant value of phi which will make V of phi as small as possible. And it could be I may take some V of phi which has this kind of shape, where this is phi and this is V of phi. And then in that case, obviously, this phi equals 0 will be the minimum value. But I could just try to play a little trick, and I could instead take this potential, which obviously is the same as this one. But now I shouldn't take phi to be 0, I should take phi to be this value, whatever it is, to minimize the potential. Okay. It also, I could try to play another trick. I could make the potential like this. Now phi equals 0 is the minimum, but the minimum amount of energy is not 0. Okay, but this I shouldn't worry about. This I can always fix to 0 by shifting the Hamiltonian by a constant, which doesn't change anything. So I can actually do that. Once you're in a theory of gravity, it's a different story, because in gravity there's an absolute concept of energy at infinity. But as long as we are not doing gravity, we need not worry about that. So these are the kinds of examples that we'll encounter. Maybe to a little bit whet your appetite, we could have a potential. Now you can think of any potential you like. This is just one scalar field. You can have also multiple scalar fields and very complicated potentials. But just imagine a potential like this. This is a very fun potential. This is a quartic, but it has a quadratic term also. And so such a graph I can have. I can choose this to be my potential. And now there are two minima. So I have to pick one of them. Okay. Interestingly, I said that as t goes to minus infinity, phi has to go to a classical vacuum. So in such a potential, it has to decide, I have to decide whether it goes to A or minus A. Okay. But interestingly, nobody has said that when t goes to plus infinity, I have to make the same choice. It might be that phi goes to minus A at minus infinity and plus A at plus infinity, or it could be plus A at both ends or minus A at both ends. All are possible. All have different consequences, and in the next 4 or 5 lectures, all will be thoroughly explored. So this is a preview of what we are going to be doing, but I hope it gives you some perspective what I mean by classical vacuum. Okay, it should just go into a minimum energy state in the past and in the future, and then I can look for any phi classical that suits me subject to that condition and do this expansion. Okay. Any questions on this?
Sir,
Yes.
Like to make analog with QM, like there are two possible classical solutions over here.
Yes.
So like
No, there are more than two possible classical solutions. There are two possible classical boundary conditions. That is, phi going to a classical vacuum is a boundary condition.
Okay.
It's not a solution. It could be a solution if I keep that to be the value of the solution all the way. Supposing phi goes to A at infinite past time and stays in A till t equals plus infinity. That's a classical solution. Phi equals phi of x and t equals constant A. That's one solution. But who says that's the only solution? That's one solution with these given boundary conditions that it goes to A in the past and in the future. There may be other solutions where it goes to A in the past and future, but in between it does something else. But it solves the equations of motion. That's our job to find. So right now I've only established that the past and future boundary conditions should be that it's a classical vacuum. And then there will be whatever classical solution you can think up for that theory. There's no general rule what are the classical solutions in a given theory. Okay, any more questions? Okay, so now to implement this, we'll start as simple as possible. Our field theory will be the one with the action with the simplest potential, which is just a mass term. And now, of course, it's clear that the classical vacuum is only phi equals 0. So in this theory, I don't have any choices. Phi has to be 0 in the past and future. Okay. Now, if you try to solve the equation of motion, as you know, is box plus m squared phi equals 0. And I want to solve this with the boundary condition that phi is 0 in the past and in the future. Then the only solution I can find, well, maybe not the only solution, the easiest solution I can find, simplest solution, is phi classical equals 0 for all x and t. So let's start with that solution. Okay, as I said, in the next few lectures, we'll explore more interesting solutions. But certainly if my boundary condition is that it's 0 in the past and future, then obviously it being 0 everywhere is a solution. It solves this equation and it solves the boundary condition, so it's a classical solution. In this case, phi classical is 0, and so phi is the same as eta. So I can keep doing my path integral without renaming phi as eta. Eta is just phi again. And again, in QFT1, effectively you are always working around such a trivial classical solution. The non-trivial classical solutions will come up, but all of quantum electrodynamics, for example, is done working around the trivial classical solution where the electron field psi goes to 0 in the past and future, and the photon field A mu goes to 0 in the past and future. Little bit more tricky than that, because A mu being a gauge field, it could go to 0 or it could go to a gauge transform of 0. It's still equivalent to 0. But that's equally good. But it's the analog of taking phi classical equals 0. That's why in your previous course, you never really encountered this split. Also because you weren't doing path integrals, where it's most transparent how to split the field into two parts and quantize only the second part. So we'll simply now repeat what you have learnt before by quantizing eta. And how do we do it? So, as I indicated, it's terribly simple. So the first thing is, so phi classical equals 0 obviously implies that S classical is 0. It's just S evaluated at phi classical. We are working now in this theory. I'm sorry, I erased it. So we are only working in this theory. Good. Okay. Now, We first ask how to evaluate integral d phi e to the is of phi. So as I said, this should have been eta. It's really eta which I always integrate over, but since the phi classical is 0, I can just keep calling it phi, so it's that. So how do I evaluate this? So this is d phi e to the is, and s can be rewritten as minus a half integral d for x prime phi of x O of x and x prime. This should remind you of things we did earlier in this course. Phi of x prime, where O, and I'll call it OKG, it's the Klein-Gordon operator, where OKG of x and x prime is box plus m squared of delta for x minus x prime. And when I have a box differential operator acting on a function of two variables x and x prime, I should tell you which variable the box is in, so I just put x. In this case it doesn't matter, but it's better to discipline to put that. So is it clear that this is the same as the original integral? How do we do it? We take this del mu and integrate there. That gives us the minus sign outside. Then there should be an I. So O should have an I. Why don't I have an I in my...
We have a I X cross, right?
yeah.
I X cross.
Yeah, but I haven't yet. Okay, so it is, sorry, I take that
So
back.
you have absorbed the I in the O, right?
Yeah, I should have absorbed I in the O, and somehow I have not. So I think there is a little bug in my notes. S is that, but I should have an extra I.
So maybe you took
Yeah.
X is equal to 1.
So I think I would like O to be this. Excuse me, what was the thing? What?
You took X.
H bar is 1, of course, but this I is there. I cannot be set to 1. So there was e to the is here. So it's e to the I times this, and s is equal to that. So I should have this where I is sitting inside O. So this is O Klein-Gordon. Okay. Now we have a sort of blind way of writing an answer to such an integral. It's a Gaussian in field space. Integral over all configurations phi. Now the boundary conditions are trivial. They have to be 0 because phi is really eta. So even if there was some non-trivial classical solution, O might depend on it, but the measure is over configurations that just start and end at 0 because they are the fluctuations. And this is phi O phi, and we have learned that the path integral therefore is equal to determinant to the minus half of O Klein-Gordon. So this is no better and probably much worse than the determinants we have been studying earlier in quantum mechanics, because it's infinite dimensional and it will be infinite, but it's useful to write it in this way. And as usual, we'll get physics out of such determinants when we compare them with other determinants. Just to give you an example, it might be that I want to compare det to the minus half O Klein-Gordon in the presence of some photon or some electromagnetic background with det to the minus half O of Klein-Gordon in the absence of that background. Okay, I might take the ratio of those two things. That might have a finite answer, even though each of the dets doesn't have a finite answer. So we keep the det and we just never worry too much about it till the time when it will be physically meaningful to us, which, as I said, will happen sometime soon. Okay, so that's the answer for that. And we call this determinant to the minus half of the Klein-Gordon operator. Okay, notice that this is for a real scalar field phi. If I had a complex scalar field, then this would be phi star O phi, and I would get det to the minus 1, not half. A complex field is just 2 copies of a real field. Okay, it's like a complex Gaussian integral versus a real Gaussian integral. So that's not difficult. Okay, so at least we've solved the problem in principle, how to do the path integral without any insertions. Okay, so the integral over this for the free theory is just that, and it's over. Okay, Let's try to do the same thing for fermions. So we simply put psi everywhere. There will be some spinor indices which I should keep, but I won't keep writing them, but they'll be there. So it will be like d psi, which is over all the components of the Dirac fermion. So 4 component things, so and they are complex. So it will be d psi 1, d psi 2, d psi 3, d psi 4 if I'm using 4 component notation, and also d psi star for each of the stars, and then s of psi and psi bar, and then psi like this. Yes.
We are not caring about the 2 pi in the determinant because
No,
it's
we are,
cancelling
yeah,
out.
we are not, yeah, it will
It's
cancel.
cancel out the-
Yeah, it will cancel. Thank you. Yeah, we could, I actually kept it quite a long time.
Yeah.
May have given you the wrong impression that it's worth keeping. Actually, it's usually not worth keeping. But you should keep in mind that you never know. Someday you might find a problem where that 2 pi is important, then you have to keep it. So somehow in field theory, we remember a lot of things that we might use, but most often we don't use them. So 2 pi is one of the least of our problems, especially since this thing is very divergent. Okay, so now this, so now okay, so this is the quantity we want to calculate, let's say. Actually, we should also allow for a few psi bars or psi stars. So there's a property of Dirac theory, which is that unless I have an equal number of psis and psi stars, I don't get any, my correlation function vanishes. I'll explain this to you maybe later when we go into more details of it, but it comes from the phase invariance of the theory, which we have already studied. For now, just take it for granted. So first let's ask how to calculate just d psi, e to the is of psi and psi bar. So this is of course equal to d psi, so d psi bar of course, and then e to the what? It is e to the I integral v for x. So now again we'll consider the simplest example. So the quadratic one. Okay. Note that this I belongs in this term. This I is a separate one. This I is in the Lagrangian. This I is the I of e to the is. Okay. And this conveniently already has the form psi bar O psi, where O is I gamma mu del mu minus m delta for x minus x prime, where this del is with respect to x. Now it's important, and O is O of x and x prime. And this I'll call OD for Dirac. Okay, so conveniently, this path integral over fermions is over a Gaussian in fermions with psi bar O psi. And this time, you know what we should get? Det of O. Det to the plus 1 of O. We saw that with fermions, the det has the opposite sign. So it's
half plus 1.
It's plus det to the plus 1 because Dirac fermions are complex. If I did this with Majorana fermions, then I would get det to the half. The problem is that in the case of scalars, real and complex are easy to distinguish. If there's one, it's real. If it's phi and phi bar are independent, it's complex. Done. With fermions, the problem is they are 4 component. Now, do they have a constraint, Majorana constraint on them or not? That depends on so many things. First of all, it's my decision. Secondly, then how is that constraint implemented depends on what representation of gamma matrices I'm using. I could say that I'm using the Majorana representation and psi is real in that representation. In that case, d psi and d psi bar are not 2 independent measures. Then d psi bar is not there. So then it's only d psi, and this is actually psi times gamma 0, gamma mu, del mu, psi. Okay, where psi is a real thing, and people also put I by 2 over here by convention, and then it will be det to the half. So, but somehow the Dirac one is the default and Majorana is special. So we'll discuss Majorana when we need it. So for Dirac. It's easier to just think of fermions which don't satisfy, a fermion which doesn't satisfy any constraint. I hope it's obvious that if I have n species of fermion, for example, electron, muon, tau lepton and whatever, then I'll get one det of O for each of them. Okay, and that one will contain the m parameter for that one. It will be like mass of the electron or muon or tau lepton. These are all different. So it will be a product of det O's, one for each of them in the free theory. So we are done with the free theory, and this thing is referred to as determinant of the Dirac operator. You'll be quite surprised if you go to Google and search for determinant of Dirac operator. You will start getting large number of mathematics references, because mathematicians have the following interesting problem. You can define fermions not just in flat Minkowski spacetime as we are doing, but on any space, even Euclidean signature space, just as in maths it's called a section of some bundle, spin bundle. And you might be interested in the determinant of this quantity, but as a function of the geometry of the surface on which you define, typically two-dimensional manifolds. Okay, so there's a lot of mathematics studying the determinant of the Dirac operator on two-dimensional Euclidean signature manifolds, which might be non-trivial manifolds. For example, it might be a manifold which looks like this. So I can define a path integral where my entire space is this. It's Euclidean and this is the space. It doesn't have any time and this is it. And now I want to evaluate this quantity with this action on such a space as a function of the geometry of this space. And now mathematicians have a lot of fun doing that. It's a very interesting class of problems. Physicists also use it for certain reasons. So you may find some physics references. You'll find both. But again, I emphasize that there's no point in asking what is det of OD if O is exactly just this, because it doesn't depend on anything. Okay, it just depends on a parameter m. But if I had a surface which was curved, then it would depend on the metric of that, then there would be a dependence. On the other hand, if I couple this to a photon, for example, psi was an electron and I coupled it to a photon, then this del mu is replaced by del mu minus I a mu. And now I have a dependence on the electromagnetic field. So I could ask, what is the dependence of this determinant on the electromagnetic field? Those questions often have finite answers. So this word is important to keep in mind, this phrase, determinant of Dirac operator. But for us, it's just a formal expression because we are doing free theory. Good. Now, the next question is how to calculate the correlation function. So we've only calculated the 0-point correlation function, that is the one with no insertions. Now we'll put insertions, but we'll go back to scalar fields. So we are back to a real scalar field, and it's this up to this. Okay. So for this, we define what I started to do a few minutes back. The more general version of the vacuum path, this is called the vacuum path integral. We simply add integral d for x, gx phi x. Now the trick here is that if I perform minus I del by del j of x, so remember, this is a functional of jy, because I take this, supposing I know how to integrate out d phi, then the answer will depend on this function j of x, right? Because the integrand depends on the function, so the answer will depend on it, and it will depend on the whole function, so it is a functional. So I can differentiate that functional, and immediately what I get is the same exponent as before times j, and I can call this point x1, then I'll get not j but phi of x1. Okay, because there is e to the I integral j phi in the exponent. If I differentiate with respect to j, I get a delta function between this x and this x1. That takes away this integral and evaluates phi at x1. But also this is an exponential, so basically the coefficient of j comes down. And that's how I bring down phi. Yes.
Shouldn't there be an integral with respect to x1?
No, no more. Because, exactly because,
That will vanish with the delta function.
yeah, so you see, this is a path integral. So after doing the path integral, so I don't know how to say it better, but maybe the operational answer is what he gave. Just differentiate this thing with respect to x1. So the differential of j of x with respect to j of x1 is delta 4 of x minus x1. Then I perform this integral over that delta 4 and phi of x, and I get phi of x1. So the integral is performed. That's the best way to see it. Okay, and if I repeat, it's very obvious. Just keep doing it. This minus I must be there every time because there's an I phi multiplying j. So minus I is to cancel that I, and I just do it n times of z of j. Then the answer is the path integral e to the I s of phi times phi of x1 up to phi of xn. And this is great because this is what I'm trying to calculate.
Only for j equal to 0.
Good. So I do this, and then I must, otherwise I would have s of phi plus j phi. So after I finish differentiating, I put j to 0. So you see that j plate, you may wonder why I had introduced an external source. There are two reasons in physics to introduce such a source. One is that really there is a source. Maybe this field is propagating in some background which I want to model as a given function j of x. Then fine, then j is non-zero. The second reason is as a calculational tool, which is what I'm doing here. I introduce it, and then I note that by differentiating this quantity repeatedly and then setting j equals 0 after finishing my differentiation, I get the quantity I want. Because of that property, it means that all I need to do is calculate zj. And then I'm done. Once I know zj explicitly as a function of j, then this procedure will give me the correlation functions that I want in the free theory. Okay, and why do I think that I can calculate zj? Well, look at it. Without that term, it was a Gaussian, phi o phi. With this term, it's still a Gaussian because I have shifted by a linear amount in phi. If I have a Gaussian of the form ax squared and I add bx to it, it doesn't become more difficult. It's still a Gaussian. So since this shift is linear in phi, it's still a Gaussian, and so I actually can do this path integral exactly in the same language of determinants. But there's an extra factor which I'll keep. Good. So this last line tells me what I should do if I know zj to find the correlation function. Okay, and of course, if I really want the normalized one, then this I want to divide by d phi e to the I s of phi. Then this one should be divided by z of 0. Well, that is z of 0. Okay, so this is the formula which will give me my answer if I can calculate zj. Now let's calculate zj. Clear? If there are any questions, please ask. Okay, good. So let's do it. How do we calculate a Gaussian integral where there's a linear term in single variable case? Integral dx e to the minus ax squared plus bx. How would I calculate this? Complete the square. So I would write this as a x squared plus b by a x. Then I would write it as a x plus b by 2a. Sorry, yeah, x. So x plus b by 2a squared So this gives me ax squared correctly. It gives me ab by, so this a and this a will cancel in the cross term and I will get bx. And there's an extra term which I must subtract for correctness, which is b squared by 2a. Huh? No, 4a. 4a. Yeah, so I should actually have had half here, sorry. Okay, it doesn't matter. This is just an example. Yeah, 4a if you like. Okay, then this term doesn't depend at all on x, so it can come out. And actually that's the answer, because the rest of it will be integral of a Gaussian. Again, I'll just shift x to x minus b by 2a, and then I can do it as the integral of a Gaussian. And I'll get my determinant. So what you can see is that the whole story with this is completing the square. There's nothing more to it. So let's do that. So s of phi plus integral j phi is equal to minus half integral d for x prime phi of x o of x and x prime phi of x prime plus integral d for x g of x phi of x. Good. So what's this equal to? It's equal to minus a half integral d for x prime. So let me write the answer. Phi of x minus j o inverse of x o phi of x minus j o inverse of x. Now this is x prime and this is o of x and x prime. And the extra term, that b squared upon a type of term, is plus half b for x prime j of x o inverse of x and x prime j of x. So it's quite tedious to write, but it's very easy to verify. The best way is to not try and derive it, but just try to show that this goes back to that. How will we do it? Let's do it term by term. So in this line, there's a phi o phi. Was that there? Yes, phi o phi. So that's there. Okay. Now let's look at the last term, j o inverse o j o inverse. Okay, so here it's o inverse j. Sorry. So minus times minus is plus. J o inverse o inverse j. So one o cancels one o inverse and I get j o inverse j with a plus. But that cancels this term. Yeah, because there was this minus. So the sign in front of that term. Now what I'm trying to do is collect this with this. So one minus, second minus, third minus, so the term is overall minus. There's a half. And j o inverse o inverse j. Imagine that these o's are matrices. Then j o inverse o is the same as j by definition of o inverse. So I get j o inverse j, and that's exactly what I have here. But here it is with the plus sign, so it cancels. So that means the term this with this is cancelled by that. The term this with this is already there, and now I can look for the cross terms, and you'll see that the cross term is here's a minus, j o inverse o phi. That's j phi. And you get another similar term from the other cross term that cancels the 2, and it's this. So I've done the completing of the square. Yes?
If we extend the matrix analogy,
Yes.
then j o inverse and o inverse j won't, like, they are not correctly placed, right? Because O is a matrix and J would be a column vector.
Yes. So J O inverse. So let's look at definitions. First of all, O inverse. Remember, okay. Let's do the definitions here, and we'll answer all your questions. So first of all, we have O of x and x prime. I've already defined that. That is the Klein-Gordon operator on delta of x minus x prime. Okay, so what is O inverse defined as? It's defined as O inverse of x and x prime, O of x prime and x double prime, integrated over D for x prime, the common index. It's just like Mij, Mjk. M inverse Ij, Mjk is delta Ik. So if I do this, I should get delta for x minus x double prime. So far so good. That's the definition of O inverse. Of course, whether O has an inverse, we still have to see, but we are hoping it will have an inverse. Okay, now what is O inverse J? O inverse J of x prime is equal to integral, so it's a matrix acting on a column vector. So it is integral D for x double prime, O inverse x double, x prime x double prime J x double. So this argument x prime is not the argument of J, but of the whole thing, O inverse J. O inverse J is a function of x prime, which is this integral. This integral integrates away the x double primes, leaving behind a function of x prime. Okay, and J O inverse is done the same way. It's like the transpose. So J O inverse of x, which occurs here, is integral D for x prime, J of x prime, O inverse x prime and x. So everything is clear. It's all by matrix analogy. If you have ever done a Gaussian integral where there's a matrix like AI, AJ, Mij, it's exactly the same. Only thing, where you sum over an index, you integrate over the coordinate in place of that. That's the only difference. And of course, in back of our minds, there's an enormous tension that any of this might just not exist. These are horrible infinite dimensional things. Any of these integrals might diverge. It's a lot of nerve to try and integrate anything over whole space, especially where space-time, when I don't even know what they are. Okay, so we have to hope for the best. But actually, in this case, some of this is at least a formal manipulation, and when we actually implement it, then we'll see the conditions for it to exist or not. So we just hope for the best. Is this clear? So now, what can I say? Well, now it's very easy, because now I'm trying to evaluate Z of J. So Z of J, because this is S plus integral J phi, so Z of J is e to the I all of this, path integrated in phi. Now look at this part. There'll be e to the this part and e to the second part. But this lower part doesn't depend on phi at all. So it comes out of the integral. So Z of J is e to the I by 2 integral T for x, D for x prime, J of x, O inverse of x and x prime, J of x prime. So exponential of I times this factor is there, times the path integral in phi of e to the I, all this stuff. So e to the minus I by 2 integral, and I'll write it as phi minus J O inverse O phi minus O inverse J, just to save myself the trouble of writing all the indices.
So I think the I will be absorbed in the O, right?
If I is absorbed in the O, then I is not there, and then it's also not here, and that's much better. Thank you. Okay? So there are two factors, one outside and one inside the path integration. Now what's the next step?
Gaussian.
Gaussian. So now this is a bit tricky because I have to evaluate this integral, and this is an integral over all paths phi, okay, and the quantity here is phi minus j O inverse. Now note that j doesn't depend on phi, O inverse also doesn't depend on phi. So if you like, j O inverse is the analog of a constant under this integration. So I can simply make the replacement phi of x goes to phi of x minus O inverse j of x, and call this phi prime of x or phi tilde of x, and then d phi, the measure, whatever it is, will be the same as d phi tilde, and so this last integral is nothing but my old friend det to the minus half of O, Klein-Bode. Okay, so z of j equals e to the half integral d for x prime over phi of x, sorry, j of x O inverse x prime j of x prime, this is a thing, times det to the minus half of O. That's the answer. And what is z of 0? Just det to the minus half of O. And what did we want to calculate? We wanted to differentiate this upper guy many times in j, then set j equals 0, and then divide by this. So when we differentiate this many times in j, it does nothing to this det to the minus half of O. So it will be left at the end, and when we divide it, it will go away, along with its 2 pi's, i's, any other things that are in it. Okay, so finally, this is the quantity that we want to focus on. And all we need to do is learn how to functionally differentiate this thing many times, which we'll do tomorrow. And then we'll have the answer for correlation functions in the free theory. And hopefully you know where we are going to go with this. We are going to find Wick's theorem, which tells us how to express correlation functions in a free field theory in terms of 2-point functions. That is, for any n, we'll be able to write the correlation function as a product of many 2-point functions. And in particular, if n is odd, then the answer is just 0. If n is even, then it's a product of 2-point functions. So we'll get that. And in the same breath, with one more little step, we'll be able to also say that what to do when we have a non-interacting theory, when we have, for example, a potential. We'll be able to express that also in this language. Now, I know that this doesn't look like the simplest thing in the world, but functional differentiation is relatively easy if you don't worry about convergence of things, and it's far easier than handling operators. Notice that nobody said anything about any operator, commutation relation, non-commuting, left side, right side, ordering, nothing like that. We simply have to learn how to evaluate a path integral over a shifted Gaussian, and we've just done it, and that's the answer. Okay. Everything, however, hinges on the existence of O inverse. If O is a bad enough operator that it doesn't have an inverse, then we have done something wrong, and we'll see what to do in that case and why that can happen. Okay, so I'll stop here.